Welcome AP Electricity and Magnetism students. I've decided to split the magnetism topic into 3 videos. Otherwise, I don't want the videos to get too long, and there's a lot of information and a lot of techniques in magnetism, so I decided to break into 3 short videos to make the knowledge more manageable. As you can see from this outline, we will be covering 3 topics today in what I call basic magnetism. By basic, I mean magnetism that does not involve calculus. So this would be like the type of magnetism that you would find on an AP test before when they had a non-calc based physics. So that's what we're going to concentrate on. The 3 ideas: magnetic field around a long wire. What we mean by a long wire is something that can be considered infinite over the dimensions studied. The concept of magnetic force, and then also motion in a magnetic field, a charged particle moving in a magnetic field. So let's get to it. Alright, so first thing, the magnetic field around a long wire, in parentheses infinite. If there was more room, I would have put infinite in quotation marks. As always, as I've said many times throughout the year, infinity is not an absolute concept, it's a relative concept. As I said in class, if you move an electron away from my finger, this distance, no one would say that's infinity, but to the electron moving out of the atom that it was formerly in, that is an infinite distance. Same thing with a long wire. We're talking about something that's maybe much larger than the distance we are from the center of the wire, like from stretching across the room, and then we're maybe like a few centimeters from the center of the wire. Alright, so if the electricity out of the wire is coming straight out of the page, coming straight at your eye, we represent that with a circle with a dot that represents an arrow coming out of the paper. The magnetic field would go around the wire like this. Now I drew lightly radius vector, and so the magnetic field is always perpendicular to all the radius vectors. So here, perpendicular, perpendicular. Now how do we figure out, first of all, the direction? Does it go clockwise or counterclockwise? We use what I call right hand rule number 1. I try to write it really briefly here and not write out in complete sentences because this is review, so I'm just reminding you of the technique. First thing you do is you put your right thumb, right hand rule, not left hand rule, but your right thumb in the direction of the current. So I have the current coming out of the page, so that's how come my thumb is pointing up out of the page. Now my four fingers, I don't know what I meant there, but basically they are in the direction of the swirl of the magnetic field. And I put swirl in quotes because the magnetic field doesn't really move. It's stationary. Yeah, I guess we could say with the swirl of the magnetic field. So it's stationary. It just tells us that the arrows are going to be stationary but pointing in the clockwise direction. A reminder, this doesn't mean that your forefingers tell you the direction of the magnetic field, because if I say, what's the field down here, you use the right hand rule. Okay, thumb up, oh, to the left. If you just say, okay, this is going to tell me the direction of the field. No, it tells you the direction of the swirl. So above the wire, it's to the left, but as we move around down here, it'll be to the right. So keep that in mind. The magnitude of the magnetic field around this long wire is given by this expression. We've seen it many times throughout the year. Mu0, here's the constant, which you don't have to memorize. It is on that reference page that you get on the AP test on both parts. And the magnetic field is measured in teslas. I'm just going to show you a couple quick examples. These are kinds of things that might show up on a multiple choice question. So I have 2 wires on the y-axis, and I want to know the magnetic field on the x-axis somewhere here, caused by these 2 wires. I don't know if it's showing up well because of the colors, but this wire, the current's coming out of the page straight up at your eye, and this wire, the magnetic fields go, the current's coming out of the page, and the current here is going into the page. So both these wires make magnetic field at this point. So first thing we have to do is figure out the directions of the magnetic fields of each individual wire. So I drew lightly a radius vector. The magnetic field caused by this wire is either going to go counterclockwise or clockwise. So these are our two choices. It has to remain 90 degrees to that radius. That way or that way. Again, we use our right-hand rule. Thumb in the direction of the current. And so we see the magnetic field is going to go around like this and go that way. So I draw that arrow for the magnetic field caused by this wire. Added to that, we have the magnetic field caused by this wire. So I lightly drew the radius here. Now my two choices are clockwise, right? Or counterclockwise. So those are the two choices. An arrow as I've drawn or an arrow this way. Which is it? Again, I use my right hand rule. So I take my thumb, my right thumb, and I put it in the direction of the current, which is going into the page like this. Right? And then so now my fingers are going this way, so the magnetic field is going to go in the clockwise direction around into the current into the page, so clockwise. So those are the two arrows. Now, the multiple choice might have arrows up, down, right, left, diagonal, right? So you've got to pick which one. Well, obviously these two are going to add to it net magnetic field to the right. So that could be a possible multiple choice question. Another example. So a little cramped here because I wanted to fit it in space. So the question is, determine the x where the net magnetic field is 0. Okay. So I have at the origin at x equals 0, I have 5i going into the page. I don't know, yeah, I could see that x. Okay, so that's good. Into the page. And then 2i, oops, I forgot to color coordinate that one. So this is with green represented by the magnetic field represented by the green arrows. So first thing I've got to do is find out the direction of the magnetic fields caused by each wire in each of the three regions. So the first wire into the page, right, like this, the magnetic field's going to be going in the clockwise direction around that wire. So what I could see is that to the right here, it's going to go to the right of the wire. In these regions, it's going to go down. So I see those, and this I drew shorter because it's further away from the wire. Whereas clockwise over here, it's going to come up, right? So there's that magnetic field. I have to find the magnetic fields in the three regions here, here, and here for that wire. So I put my right thumb in the direction of the current coming out of the page instead of into the page. So out of the page. And I see that now the magnetic field is going to go around that wire in the counterclockwise direction. So over here, it's going to go down, and over here, it's going to go up. So you see those green arrows. So back to the question, we're looking for where the magnetic field the net magnetic field is 0. Cannot be 0 in the middle, right? These are both in the same direction. They can't cancel each other out. That leaves these two regions. Only this one is possible. Because over here, this up arrow is always going to be longer than this down arrow. This up arrow comes from this wire. We are closer to the larger current. So for this arrow, we have a smaller radius and a bigger current. Bigger numerator, smaller than always a bigger answer over here. They cannot balance out over here. Over here, this larger current is at a larger radius. So larger current, larger radius might, in theory, come out to have the same magnetic field as this smaller current, smaller radius. So it's somewhere to the right of that second wire over there. So I have to apply this formula and set the magnetic fields equal. Now I left off some steps here because again, so first thing I would write is B5 equals B2, maybe something like that. And then I fill in the currents and R's here. So the current for this wire is 5I, and the radius, well, if this is x equals 0, this point is x away. So 2 pi r right there, with r being x. Now in this wire, I plug in the current here for, right, mu 0 I, which is 2I. What is the radius? Well, if this is x and this is d, what I'm doing is I'm taking this larger distance x and subtracting off D. Oops, did I? Yeah, I have it backwards. Oops. So, time to fix X minus D. X minus D. All right, so that's the setup. And then you would, of course, just solve for the X, okay? But as I said throughout all these review videos, right, we're going to try and focus on the main ideas and the setups and the techniques and not get too bogged down in the details. Okay, best way to prepare for the AP. Okay, moving on. Magnetic force. Alright, so wires make magnetic field. By the way, so do permanent magnets, but permanent magnets really aren't in the AP electricity magnetism curriculum. But permanent magnets also, they are iron atoms or other materials in which the orbits of the electrons in the atoms create the current. So, well, yeah, so then by the right-hand rule, well, with electrons you go the other way, then you'd have magnetic field going through the atom. Also, electrons have an intrinsic magnetic moment. They say that they're said to have a spin to them, so even a single electron is like a little tiny magnet. So the same concept of current creating magnetic field is also evident in permanent magnets. All right, well, but let's go on to what's in the curriculum. Magnetic force, okay? So remember that magnetic force is caused by a charge moving through a magnetic field. Unlike electrostatic force, F equals QE. You only need charge and you only need electric field and you'll have force regardless of the motion. In the case of a magnetic force, as you remember, you need a charge and a field, but you also need velocity. A stationary electron next to the world's most powerful magnet will not experience a force. It has to have velocity. Furthermore, the angle between the velocity and magnetic field cannot be 0 or 180 degrees. It has to be some other value. Maxes out at 90 degrees. So here's scenarios. Magnetic field going into the paper. You got a velocity to a proton and an electron moving. First of all, the magnetic force, you figure out the direction through another right-hand rule. I say right-hand rule number 2. So again, I just sketched it out quickly because we're just reviewing. But a reminder that the first thing you do is you put your index finger in the direction of the velocity. So see, I got velocity going this way for both the charges. Then I put my 3 fingers in the direction of the magnetic field. Well, fortunately, my 3 fingers are already going in that direction. But if the magnetic field were coming out of the paper, then I'd have to swivel my wrist, keeping my index finger forward, but swivel this way and have magnetic field coming out of the paper. But it's going into the paper. And now my thumb, and I want to remind you, the right-hand rule, right? Not the left-hand rule. So sometimes people, as I joked in class, they get messed up. They start using their left hand. So my thumb points in the direction of a force on a positive charge. Okay? On a negative, the force is in the opposite direction of my thumb. So it goes down. There are other right-hand rules. There's one that goes like this, but, you know, if you want to look them up, you can, but I don't want to get too bogged down and confusing here. But cross vector cross product or QEB sine theta. All right. Also, when you have a wire through a magnetic field, with current through a magnetic field, that's also moving charge creating force. It's the same right-hand rule. Velocity or current, magnetic field going up at this angle, and you see my thumb points out of the paper. So I have the magnetic field with a vector with a dot with a circle around it. The formulas are IL cross B or ILB sine theta. One little example tucked in down here is calculating the torque on a wire. I got a wire loop here, dimensions 0.3 by 0.2 on an axle. And I've got a current of 5 amps going around here. and a magnetic field going like this. Okay? So the first thing is that by finding the torque, I got to think about the forces. This and this, the current and the magnetic field are 180 degrees apart from each other, giving me zero magnetic force on this part of the wire. This and this, we have the current in the magnetic field 0 degrees, giving me zero force down here. There's a force here, but it's at the axle, so that's not going to make a torque. Only right here is a torque generated on this wire. And by the right-hand rule, current, magnetic field, okay, thumb is going into the paper. So there is a force. I won't put it right on the wire because then it's kind of hard to see it anyways, but it should be on the wire technically, like even here, but it's hard to see. So there is a force at a radius, and there'll be a torque. So the first thing is we got to find that force, ILB sine theta 1. This theta 1 is the angle between the current and the magnetic field, which is 90 degrees. I just plug in everything here. The 0.3 meters, the length of the wire, 0.1 Tesla, 90 degrees, and I get 0.15 newtons. The torque now is RF sine theta, but the theta is not the theta between these two, but the theta between radius and magnetic force, which are also 90 degrees, right? Radius is this way, force is that way. Well, it's 90 degrees, right? So that's also 90 degrees. So RF sine 90 gives me my torque. So there's an example of torque caused by a wire loop in a magnetic field. Moving on, last thing for this little subtopic is what kinds of motion are possible in the magnetic field. And what I'm talking about motion is like a free particle, not a wire like in the case here that's stuck on an axle. No, I'm talking about throwing a single electron or a single proton or an ion through a magnetic field. First thing in general, if the velocity and the magnetic field are parallel or anti-parallel to each other, since theta is 0 or 180, we get zero magnetic force. With zero force, the particle will fly at a constant velocity, meaning constant speed and constant direction, straight line. So that's the thing, straight line. Okay, maybe I should write that. Constant V means straight line motion. Okay. If the velocity and magnetic field are perpendicular to each other, then what results is circular motion, okay? Because the velocity, magnetic field, and so the force is always perpendicular to velocity. Velocity this way, force that way, and then it causes a circular path. Also, a reminder that the work done by the magnetic force as it goes around in the circular path is zero, because if you plug in force times the displacement, instantaneous displacement, or for little dx, the angle between the force and the motion is always 90 degrees, so the work formula Ft cos theta is zero. What that means, if there's no work done by the magnetic force does not change the kinetic energy on a freely projected particle. In other words, it goes around in a circular motion at a constant speed. The other possibility is if the velocity and magnetic field are not perpendicular to each other, so they're not 90, but they're also not zero. So maybe they're like 30 degrees apart or something. What results is you get a helix. A helix is circular motion superimposed with linear motion. In other words, like a spiral, like a DNA molecule. You've seen the pictures. So again, work is zero by the magnetic force, so the speed is constant. The velocity is not, because it's turning. So that's the general patterns that are possible with a freely projected particle in a magnetic field. Another application is the mass spectrometer. It's a device used to measure the mass of things, or maybe even the charge of particles. You can use it for any number of things. So let me just explain. So generally, the most thorough mass spectrometer is comprised of three regions. There's a region which you use the voltage to accelerate a particle, like maybe an electron. I know that the particle is negative from the polarity of the battery. This is the negative side of the battery, so it's going to repel what? A negative charge. If the battery were the other way, flipped around, then I would know that this side is positive, so it would shoot positive ions. Okay, so you tell what the charge is from the polarity of the battery in region 1, or the voltage source. That accelerates the charge, gets it moving. This is what we call the velocity selector region. The key idea is there's a magnetic field and an electric field that are perpendicular to each other. And I forgot to have the magnetic field still exist over here. So maybe I should highlight that. Okay. And what that does is it creates two forces that oppose each other. And by the right-hand rule, if I use my right-hand rule, velocity, magnetic field going into the paper, my thumb points up, that would be the force on a proton, or positive charge. So the negative charge feels the force in the opposite direction. And then with the electric field down, the electric force is in the opposite direction of the electric field. So we get two opposing forces. If something is moving faster than what we desire, QVB sine theta will be greater than QE. And so this will have more magnetic force curving it down. If something is going slower than we desire, this will be shorter than this, because this stays a constant, doesn't depend on velocity. So slow particles, this is smaller, and so this will accelerate upward with electrical force dominating. So just right velocity, those two are equal, they pass through. That's why we call it velocity selector region. Here the electric field is gone, so the magnetic force is the only thing that continues to exist in the downward direction, causing circular motion until we hit a little detector over here. A reminder that the radius here is 1/2 the diameter. Sometimes that comes into play with problems. They'll say how far away a detector is. You got to remember, oh, I got to divide that by 2. All right, here's the physics. In region 1, where the particle is accelerating, we can use just simple energy conservation. We've got electrical energy here, and then it becomes kinetic energy over here. In other words, electrical energy QV, voltage 1, that's the electrical energy, is equal to kinetic energy. And we've got a relationship between the voltage of this power supply here and the speed of the particles shooting through. But as I said in class, this is only an approximate speed because the particles don't start at 0 velocity. They're moving thermally. So this is only going to be an approximate speed because we're assuming V0 is 0 here. It's not. So these come in with a whole range of velocities here. In velocity selector region, because we can adjust this electric field with another volt power supply, turning a dial, we could turn up the electric field or turn down the electric field, increasing or decreasing this force. For just the right velocity, those two forces balance, and then the thing goes through with 0 acceleration, constant velocity. So we could figure out the velocity maybe by setting QVB sine 90 equal to QE, electric force equal to magnetic force. And then the charge of the particle goes away, and we've got an expression. So by altering these fields, we can pick different velocities. We could alter the fields with electric currents for magnetic field, or voltage with a couple plates, varying the electric field with a power supply. And also a reminder that the electric field could be the voltage between these two plates divided by the distance from V equals ED. Divide the D over and you get the electric field. So that's another possibility. You know the voltage over here, you could substitute that in. So there's the physics for the second region. And then for the third region, we have circular motion. The centripetal force is caused by the magnetic force. Okay? And so centripetal force in general has to have mv squared over r. Magnetic force is QVB sine 90, which I left off. One of the velocities goes away. We have an expression here. If we measure the radius, we know the velocity from over here, and then we know the charge of the particle, because maybe it's an electron or proton or ion of some sort, and we can adjust the magnetic field with certain coils. We can measure the mass of the particle. It's why it's a mass spectrometer. But anything can be unknown. If we know the mass, Maybe we want to know the charge, so we just measure everything else. This equation, whatever the application is, means that you know everything but a particular unknown you're after. But there's the physics of the three regions. Okay, so there is magnetism subtopic A, basic magnetism. We learned about the magnetic field around a long infinite wire, a little bit about how to find the net magnetic field. You got to do a vector sum of some sort. The magnetic force, QVB sine theta, ILB sine theta in the right-hand rule. A little application here, torque in a wire. Then we learned about motion in the magnetic field, three possibilities. Okay, straight line, circular motion, or helix. And mass spectrometer with its three regions, okay, and the physics behind each of these. All right, so that's for today, or for this subset. All right, I'll see you in the next review video on the BioSavart law.